see who we have over here. We have Physis. Physis in the back. University of Bologna. Yes, looking good. Técnico Solar Boat and Energy boats teams. Técnico, Portuguese team. No, okay. Aha, yes. Beautiful. Team Sea Sakthi. Back there. Elettra, Genoa. Perfetto. Antwerp. I saw them. And Instituto Superior Técnico. Perfect, we have them as well. Okay, let's give a few words.
Okay, ladies and gentlemen, welcome. So, we are going to start our first tech talk this year. This is the 11th edition of the Monaco Energy Boat Challenge, and I'm really happy to have you all here. This year, we have a little change. So, all the prizes are separated for a different individual day, and today we will start with the Innovation Prize. So, first of all, I would like to invite Jeremy Lagarig, the head of jury, to tell a few opening words for this nice Tech Talk event. Thank you very much.
Thank you, Szilárd. See you again. I hope you had a good technical inspection and a good first sea trials. Maybe in the harbor because outside the waves was a bit choppy. Anyway, we are here tonight on the Tech Talks. You see that the configuration changed compared to last year, but the spirit does not. The idea is always to promote the best innovation we are seeking with a fantastic jury with me. The idea after this prize will be to give you a grant, some money, but also to give you the opportunity to introduce your project to some companies that might become investors and shareholders in your companies that you want to launch.
The idea is to push boundaries to try to create a real innovation that help also the world of the yachting, the world of the boat of tomorrow, in order to have a better future, to try to save CO2 emission, to try to save the quality of the water, and to try to save the next generation, let's say, marine and also what we have on shore. Basically, very proud to see all the projects. It was quite difficult for us to select the 6 finalists that you are in today. We had one big discussion around one project that is not qualified here, but anyway, you know the configuration of the tech talks. You have 10-minute presentation. In these 10 minutes, we need to know who you are, what's the project of the innovation, and how you want to develop it, and why it is so useful that we select your project. After these 10 minutes, you will have some questions from the jury member for 5 minutes. And after those 5 minutes, you will have grants. Each jury member is giving a grant in between 1 to 10, with 5 different classifications. The impact, what is the objective of the innovation, if it's really useful, and if we see that there is a real proof of concept already existing. After all those we will be able to give you on Saturday night the classification about the winner of the Innovation Prize. And in the coming weeks, if we are very supportive to your project, we might introduce you to some potential investors. I hope you are happy about the presentation, and all the best, and looking forward to see amazing innovation. Thank you so much.
Our first team we are happy to welcome on stage is our lovely Milanese representative. So please, Physis, Polimi, up on stage. Thank you.
Is it a command? Okay. So, hello everyone. I'm happy to be here to present our journey into innovation. I'm Alessandro Paier, the Electrical Technical Director at Physis PEB.
And I'm Enrico Alberti. I am the coordinator of the Software and Electronics units in Physis PEB.
So, For our team, innovation is reflected both in research and development activities and solution-wide, project-wide solution mounted on board of our hybrid catamaran, Ione 3.0. We are going to talk of what we consider our main technical innovation, which is our brand new project, Physis Energy, and then flexible power management with proprietary electronics and real-time server-based telemetry. So, we spent 3 years designing intelligent hydrogen management system, and this gave us the solidity and strength to take a leap into science and design a manufacture, which reflects in our proposal to design and manufacture a brand new PEM fuel cell with innovative materials, increased efficiency and durability, and reduced life cycle assessment and operating and maintenance costs. So the underlying concept in our fuel cell is the innovative bipolar plate and gas channel shape. Our bipolar plate here is represented into a picture of our prototype, which is 100 square centimeter bipolar plate. Bipolar plates are the component that ensure the thermal and electrical conductivity between the layers of a stack. Okay. Our is made out of graphite, isostatic graphite, to increase the thermal management, and the gas channels are made with an interdigitated and sinusoidal geometry to enhance water management and reactant distribution along the whole plate. Back to the origin of our project, we made a few preliminary studies, first in 1D modeling, and then we self-developed a CFD model, both for the single channel and whole layer performance evaluation. So here you can see a significant parameter for our fuel cell stack, which is the mass fraction of oxygen at the cathode side, due to the sluggish reaction rate it has. So you can see there is the single channel geometry, which eventually the best, the optimized geometry was the 0.25 rib to width ratio, which the ribs are the staggered pattern within the channel. And this is our parallel configuration channel, where you can see the inlet and the discharge outlet of oxygen over here. And you can see that the oxygen is really distributed homogeneously along the plate, except for the distributed channels. But I won't spoiler the whole project, because it's also competing for the Sustainable Yachting Award, and we are going to talk deeper tomorrow about that. Here you can see a few results that we obtained at least 1 month ago with the simulation for our first geometry proposal. And you can see we can reach a peak power of 32 watts with just a 100 square centimeters layer. With an efficiency that ranges up to from 40 to 50%, resulting in 50% lower hydrogen consumption, taking into account our 72 layer fuel cell stack made from a third-party company. Okay, and we are talking always with same stack size, comprised of 72 layers, but with our 100 square centimeters, okay, of bipolar plates. So really lower compared to our fuel cell stack size. I was talking about focus on innovative materials, thanks to our main sponsor, ScienceCo. In fact, graphite bipolar plates don't need any PFSA anti-corrosion coating. And also for the MEA, which stands for membrane electrode assembly, okay, the one that is put between the two bipolar plates, okay, between anode and cathode side, are made with science co-patented aqueous water-based solution. Whereas for the casing, we are going to use recycled and 3D printed or composite materials, and all of this solution at the end lead to lower operating and maintenance costs, higher performance, and lower life cycle assessment. Here you can see a picture, okay, a rendering of our prototype stack that we are going to test further in the next month. You can see the 3D printed materials for the end plates, which are the orange one. This is the cathode, this is the anode, left-hand side. And there are our bipolar plates with the sinusoidal interdigitated configuration, and MEA with the GDL, which stands for gas diffusion layer, which is a key component to distribute homogeneously the gas along the electrode. Now we'll pass the word to Enrico.
Okay, so now we can talk about a bit on what's actually inside our boat right now, what are the innovation that we have made this year and that are currently running inside our boat. So one thing is that now in the boat we completely control our PEM fuel cell with proprietary electronics. That means that we removed everything that was a stock with the fuel cell, and this is really important for us considering what Alessandro just said, because if eventually we're going to build our own fuel cell, we know that we have the experience and the knowledge in order to control it properly, since we are doing it now with the current fuel cell. Another thing is that our system right now is able to compute the optimal power output and to split the power in the best efficient way, considering the current state, in this case of the endurance race. Yes, the system has the knowledge of how much time it has. The best way to split the power is computed and then is provided to the system. With also the possibility, since it's completely controlled by electronics and our software, to be able to charge the battery when it's actually needed. And obviously, in case that we have any kind of faults and emergency, we have, again, with our electronics and software, in a few milliseconds can react and understand what's the best way to control the system in order to keep running, but still being safe and not putting the fuel cell in danger. Another thing that we did implement is a real-time server-based telemetry and remote computation. So we actually run our own server that is able to, in real time, compute the best power split, knowing what's the current data that the boat provides, compute the power split, considering from a single moment to the end of the race, provided to the onshore team, and also provided to the boat where the power split is applied. And also obviously we do have every kind of every possible data point that we can see, and we have automatic detection of faults, and also constant knowledge of the operations that our electronics is doing to control the fuel cell, to control the system. So yeah, that's it for our innovation presentation. Thank you.
You now have 5 minutes to ask your questions.
Okay, I can start from the jury question. You say that thanks to your innovation, maybe I will go a bit more in details, but this is our job. Could you explain why this is more efficient? And you are speaking about 50% efficiency, while on the market we already know some fuel cells that can go up to 65%.
Okay, so for proton exchange membranes, what our experience is with our open cathode stack, that is a compact solution for the Monaco Energy Boat Challenge. We are ranging up between 45 and 35% at high power outputs. Okay, and as I said before, with our prototype, okay, with non-optimized distributor for the reactant, we reach up 50% efficiency at a considerably high 30 watts per layer, just with 100 square centimeters. The innovation itself is not the efficiency, which is just a consequence of the revolutionizing geometry for the bipolar plates. As I said before, I will not go into further detail because I want not anticipate for tomorrow, but we are working also on the distributor side for the reactant with an empty chamber and dot mixed and dot matrix for the optimal distribution of the reactants, and which is going to increase over and over efficiency. So yeah, the main innovation is the configuration of the gas channels for the reaction, which is something that, as I stated in the proof of documentation paper, which I submitted, is something that was only used for research and development and not for a target component that was scalable for the market. So we are going to hopefully design a stack that is ready to use for the further generation for this team and to be tested here in the Monaco Energy Boat Challenge one day.
Could you please explain what will be the schedule, the development schedule you anticipate with the company you are partner with your university, and when it will be implemented, how many tests you will do before you perform, and maybe coming here next year with a new fuel cell?
So I think that the ballpark for seeing our first completed fuel cell stack with integrated electronics, both power and console-wise electronics, will be at least 2 years. But next year we're going to plan to promote our new geometry, okay, with the final bipolar plate geometry and the stack itself, okay, but without any electronics connected to or the reactant power supply and everything else, just the stack with the final configuration and the final MEAs. But within 2 years, we're going to tailor-made to design our new tailor-made electronics and power electronics also, in order to be ready to control every sensible parameter of our fuel cell stack.
So I would like to go back to the question. If efficiency is not really your goal, what is the advantage for the consumer? So what are you really having as a main objective? If it's not efficiency, what is that?
Okay, maybe I was not clear. Yes, efficiency is one of the targets, okay, and is consequent to the our new geometry development. But taking into account, I made some calculation on the fuel cell, on the hydrogen refill savings using our current geometry that is not finally optimized. Taking into account what are our consumption rate of hydrogen during, I don't know, endurance races as well. I can finish. Okay. You can save roughly 0.5 90 cents per hour of using our fuel cell stack.
Thank you very much, gentlemen from Physis from Milan. We're following up with the second Italian team. We're welcoming the University of Bologna Argonauts team on stage.
Okay. Good morning to everyone. I'm Alessandro Gaggioli. I'm a member of the powertrain department of the Unibot team. This year we decided to bring our power system from 38 voltage to 96 volts. This because we have the issues to build a hybrid powertrain high voltage system. Our goals was that we need to improve the efficiency of the systems with the same power but with less current, a significant mass reduction given by smaller components and thinner wiring, and then to give a boost of the performance of the boat with more power. And the longevity of the system. Our BMS constantly monitors the state of the batteries and prevents a deep discharge of the batteries and all the states of the batteries. Regarding to the market potential of this system, the 96 volts is a territory that is uncovered on the market, because there are very few alternatives that are open since last years, and we think that for small and medium boats, there's a really space on the markets that wanted to bring. They want to bring also performance, but minimize the cost. So our system is also usable during the racing or the simple cruising for other people. We focus on the use of readily available components because we focus on the smooth transition from the prototype that we made to the mass production. And this also brings to accessibility to a wide range of customers, and you can look to sort of pricing structure of our power system. So, as I said before, the applicability, the scalability is the main focus, because our BMS is scalable to any voltage from 38 to 144 voltage, only substituting some components. And the modular approach that we made consists in ensure that as the demand grows, the production of the BMS and the power system can scale accordingly. Our focus is also on the use of the materials, because all the components that we use derive from our colleagues in the Motor Valley of Bologna that were used in different contexts. So we make a lot of trials with these new hybrid systems, and we saw that we increased the speed of our boats also with an Eiger power motor that was impossible with the previous power system. And also we could stand with a prolonged use of the power system because we have a significantly efficiency losses. And also we check the robustness of the electrical environment by electrical failures and all the electrical failures and environmental hazards. Thank you so much for listening.
Five minutes for questions.
Are you thinking to go to the market with this product?
Maybe there's not a really project on the market, but our idea is that all that we thought is to an idea that it's possible on the market.
Because you were referring, in fact, to small and medium-sized boats, so that's what you were.
Yes, because we think that our solution is optimal for the medium and smaller boats, because it's not our outboard engine is not compliance with higher boats.
So you are talking about how many kilowatt on the?
Up to 30 and more kilowatts.
Okay, thanks.
Thank you for your presentation. Why do you think 96-volt systems aren't more popular than they are? Why do you think 96-volt systems aren't more popular?
Because we checked the market and we saw that there are only two outboard engines, not 96 volts, that get out from last years, even 2 last years. So the main market is only about 38 voltage.
But why do you think that is? Is it safety reasons? Is it reasons, technical reasons? Why?
Maybe it's more difficult to bring up this voltage.
I think your solution is interesting, switching, so increasing the voltage. One question was similar to the one of my colleague of what is changing when you're going to 48, 96, 144? May you have safety issues? And the other question is why you speak about a modular system? Because once you have the complete system with 48, 96 or 144, you don't change only the batteries, but I guess you need to change the whole system.
Yes, so it's true that with higher voltage the safety is decreasing. The module is regarding to our BMS, because we only substituting the components, we can adapt the BMS for every tension.
Thank you. And last question to reflect about the spirit of this one. Would you consider having this BMS open source to share to other university or other students, or you would rather create a company to develop those BMS?
I don't think that's on my choice. My choice.
I have
one of our results. It's a little bit outdated, but we see in the x-axis the fuel cell velocity, but it can also be the fuel cell power. In the y-axis, the battery velocity or battery power. And then we have the number of flaps. As you can see, in the middle part is where we can obtain the maximum amount of flaps or distance traveled. So first of all, this works by trying to interpolate through a cubic spline some of the velocities of the vessel, some of the drag of the vessel for different velocities, the power of the fuel cell and the battery. This is because, as you know, functions, at least for computer, are discrete functions. So we try to make it continuous. We then we use derivatives to try to find the maximum number of flaps for optimization. And we can compare it also for different accelerations. This means that we can compare it, for example, for a constant acceleration, for acceleration that goes linear with time, or in fact, any type of acceleration. And then this can also be modified to your accommodations. For example, it can be adjustable for all the yachting industry. We can, for example, with time and distance, try to predict the amount of energy that we need. And for example, if the conditions change and we need to go to land to refill because, for example, the seawaters change rapidly or anything else, we can also update the pilot so we can go to land.
Having the digital twin is nothing if we don't know the actual fuel consumption of our prototype. So in order to do that, we applied the oxygen balance method, which derives fuel consumption from the difference between oxygen concentration at the inlet and exhaust of our boat. And it can do all of this without no modifications to the balance of plant. This was applied to our prototype in collaboration with the EN Plus Lab in Técnico, our university, for a master thesis, which is my master thesis. So why is this important for us and the industry? The ISO international standard predicts 3 ways to certify energy consumption, and all 3 of those ways need modifications to the hydrogen line in the vehicle, either in its software or hardware. So this technique allows for the measurement of energy without any modification and thus without manufacturer intervention. So what does this look like for us? Here you can see the diagram of the cathode systems in San Miguel 02. San Miguel 02 has a flow meter already installed, which is able to export data. So the air intake we can take directly from the boat's software. But in case of a vehicle where the flow meter is not accessible, or maybe there is none, we can derive the air intake by doing a nitrogen mass balance. At the exhaust, it's where all it's concentrated. We have a water purge to condensate all the water that may interfere with any probes and sensors, so we have good readings. And then we have a set of sensors. I would like to point out that I forgot in my hurry to put a pressure sensor in the diagram. It's missing, but I want to mainly point out the hydrogen. We have a hydrogen probe to detect crossover from anode to cathode, which happens in all fuel cells, so we can take that loss into account. And the probe used to detect the oxygen, it's the same probe that's used to detect carbon emissions and energy consumption in internal combustion engines. So this equipment is already widespread and there's no need for new fancy equipment. So here are the results. Unfortunately, we could not bring you a whole performance curve of our fuel cell because our water purge behind the sensors, remember what I said, did not work well. Our flow meter did not like water particles flying around, but we were able to take 2 data sets, 1 for each power. So here you can see the oxygen pressure at the intake, of course, is constant, 21% oxygen in the air, but at the exhaust it varies according to the fuel consumption. As we can see, of course, the number of moles of consumed hydrogen are 2 times the moles of oxygen, so this relates to the instantaneous hydrogen consumption you can see. I want to add that it may need to be applied a time correction if the vehicle has a long systems, but in the case of SCM02, it was not needed because it's very compact. So here we have the accumulated fuel consumption of the previous graphs. We have a 20% deviation from beginning of life conditions that were supplied from the manufacturer to us. Validation with the pressure method did not stand valid because of the equipment we used. Our manometer is an analogic one. It did not detect pressure fluctuations well. So, of course, future work is the proper validation to know which is the real deviation from the actual hydrogen consumed. Of course, 20%, it should not be strange because our fuel cell is already old and it has a lot of hours of use, so we should expect an efficiency drop. And of course, we must obtain a complete curve by doing the water condensation more thoroughly at the exhaust. So, of course, I want to thank again the N+ Lab for all the equipment and help it lent to us, and of course my supervisors, Professora Patrícia, Professor Gonçalo, and Miguel.
I do have a question on the water purge. Is the water purge you are using the one that you were introducing to us last year?
We started by doing that, so it was not enough. At the exhaust of the fuel cell, there was a lot more water than we had at the anode. Now we are working in developing some solution with copper tubes or aluminium tubes and some ice to really condensate. I already did some testing before I got here, before this, and it really was condensating a lot more and not creating so much problems with water droplets. But I think the solution may need something more serious and more aggressive, like ice and all those stuff.
And do you think that by your digital twin, you will be able to implement the example of the fuel cell of your colleague from Physis, for example, to simulate the result of these kind of solutions?
Oh, yeah. One of the things with our digital twin is that it's really like modular, so we can change any type of, for example, the fuel consumption of other fuel cells, anything like that. It just only needs like some values, like the energy, as I said, the fuel consumption with the fuel cell, and that's pretty much what it needs. So it can be changed completely.
Question on this digital twin. It's a nice idea. I have two questions. How did you use this digital twin for your project, and how did you validate it?
Yeah, we are using it. We'll use it for especially the endurance race, because it's like it's where we will be using all the energy and the fuel cell and the battery. To validate the data, we unfortunately, at least now, the master thesis of my colleague is not correct, so the data is really rough still, because we are using the fuel consumption that has a big error right now from the manual because of the old age of our fuel cell. So at least now we can't really validate it. We just tested it, and it got an around 20% error, the same error of the fuel cell consumption. So we don't really know if that's all the error that we are getting, or from the simulations of the drag. Unfortunately, that's still an issue, but I'm hoping that with the master thesis, I can get a better result.
I guess that in between that there is also even more, not only fuel cell and drag, but there is also transmission, propeller, and all that kind of things, and the design of the whole system.
Yeah. We are also accounting that. We have an efficiency for the propeller. We put around 50% of efficiency, which is much less than the manufacturer gave in the manual. So yeah, we are always trying to shoot under, because it's the safer option. But yeah, it still needs a lot of testing to make the best approximation.
Yeah, thank you for your presentation. Does the digital twin take into account things like external factors like weather, waves, wind, things like that?
Yeah, we take into account seawater currents, for example. Waves, I couldn't really approach that problem yet. But yeah, seawater currents we have into account. And that's really all that's really all the external factors that we are still taking into account. I mean, it still needs a lot of work, but yeah.
In the past of my career, we designed the software that we sold to the America's Cup. This was not possible before we reached less than 2% difference in between the digital twin and the real life. Could you give us an idea about how many development we need of your software before being able to be closer, let's say, less than 5% difference in between the digital twin and the real life, and how you want to apply that in the yachting industry, because that's also important in our graduation.
Sorry, I couldn't really understand.
When do you think you will be able to go to 5% efficiency in between real life and the simulation?
When?
And the second question is, how do you think that will be able to be implemented in the yachting industry? For example, Gilles, my colleague, is designing big yacht. He might be interested in your digital twin to simulate the consumption of his yacht.
Yeah, really quickly, for the second question, I think it's easier to explain it. But for example, at the yachting industry, we can, for example, as you know, having like, for example, a hydrogen boat, it's really expensive if you have a lot of tanks. So if you can predict, not of course that we need to always give a bigger amount at what you will need, so that unpredictable events don't happen or don't affect us. But we can, for example, predict the amount of energy that we need to travel, for example, to, I don't know, any place. For example, I know that in the aviation industry, it's really common for the people to sell private planes and saying, oh, you can travel until this area. So the yachting industry, I think it's also possible and also a good implementation. For the first question, sorry, to be honest, in terms of time, it's really difficult. We need a lot of testing yet, but to 5%, I would say, it's a difficult question, but 2 years, 2 years, I would say 2 years.
Okay, obrigado, Team Técnico Boat. We're welcoming our lovely Indian friends, Team Sea Sakthi, up to the stage. Or will we welcome the solar boat team of the Portuguese Técnico Solar Boat? Sorry, I apologize.
Hi everyone, good afternoon. My name is Miguel. I'm the current team manager for the Technico Solar Boat team, and my colleagues Pablo and Francisco are from the Mechanical Systems department. Technico Solar Boat, like my colleagues from the Energy boat showed earlier, is a team of students from 2015, founded in 2015, that constructs renewable energy powered vessels to compete in international competitions like Monaco. We have competed in Monaco since 2017 in the solar class, and since 2021 we've also appeared in the energy class working with hydrogen-powered vessels. We've won a second place in the solar class in 2019 and the third place also in the solar class in 2022. More recently, we also started working in the autonomous sector with fully unmanned autonomous boats. The boat we are bringing to the Solar class this year is not new. It was constructed actually in 2021. It's codenamed São Rafael 03. It's a trimaran, carbon fiber, and it's one of the few boats that have an electronic control, hydrofoil control. So it has 3 stepper motors, one for each hydrofoil that actively control the flight of the vessel through different conditions. This control has different modes that we have implemented this year for each race, adjustable height and reactiveness, and as I said, fully automated control to adapt to different weather and water conditions. We've also started working, and this year we've implemented a new battery and a new battery enclosement, a new battery box, that fulfills our need to have fully waterproof enclosements and boxes for the vessels. Since in 2021 this boat capsized twice, and we've had the need to start working in waterproof boxes to protect ourselves and our boat. And finally, just to finish my part and to give my colleagues a little bit of insight into the innovation project, we also have real-time data viewing with fully personalized apps for computer and smartphone, and to have telemetry on port while the boat is on water. This also applies for the energy boats. And now, my colleagues.
So, this is the new hydrofoils of São Rafael 03. And here we have much more than just a beautiful design. Actually, the most beautiful part of the design is the algorithm behind it all. With this algo, we can actually optimize the whole hydrofoil configuration in order to maximize velocity to reach a specified distance or to reach a specified discharge time. So let's imagine, if we input 4 hours discharge time, this algo will give us the hydrofoil configuration that allows São Rafael 03 flight at the max velocity possible in order to deplete the battery in 4 hours. By this, we maximize the distance covered in endurance or any other trial. It's just a matter of defining your discharge time. So this algo is actually pretty modular, so we can actually model any kind of vessel with any kind of hydrofoil configuration and optimize any design parameters that we want. It's just a matter of run the model through all the parameters and then see the one that delivers the max speed and match with the opt power. So, actually, before we talk about the complex aerodynamic stuffs, you need to understand one simple thing about how wings work. Kinetic energy deflection. So, all wings, all airplanes flies just because of it, of course, in a fundamental way. So, to understand this, let's imagine the wing is just a flat plate underwater or inside a fluid. And then you add some velocity to that flow and add some angle of attack to the wing. So let's imagine the flow will hit here and will be deflected down there. And that deflection actually creates a resultant force with this vector right here that we can decompose in 2 main components. The lift component, the vertical component, that's what actually makes things fly. And the drag vector, the horizontal vector against the movement, that's what spend our fuel. So, as hydrofoil designers, our goal is to optimize this lift-to-drag ratio. And then, in order to do this, we implement all these complex shapes that you can see right here. But fundamentally, that's just one thing happened here, kinetic energy deflection. So, keep that in mind.
So, as long as flow sticks to the wing and curves around it where you want it to, everything goes according to plan and we can fly. But sometimes that's just not the case. Sometimes instead of deflecting, flow just goes on straight ahead, detaching from the surface of the wing. And that's exactly what was happening in our older design. We were asking too much for the flow to do, and flow was actually separating from the surface of the wing and curving backwards, creating vortices which further increase separation, and after all of this snowballing effect, we lose about 50% 50% of our total lift, which makes our hydrophiles work overtime to actually get the same lift and causes stability and efficiency problems. Our first objective was to minimize this messy and unpredictable phenomenon by first optimizing the 2D shape of the wing, giving flow a much nicer curve to follow along the entirety of the wing. And by adjusting the parameters according to the optimization algorithm, we managed to cater to our own needs and improve efficiency. Since the center of the wing is the biggest, most important, and most problematic part, we also wanted to protect it as much as possible. So we increased the root chord, we twisted the wing, and redesigned the interface piece so that flow has a much easier time adapting to the curvature.
So before I talk about the algorithmic structure, that's one more thing that you need to understand. We do not need to work with the design speed because the design speed depends on the hydrofoil configuration. And actually, each hydrofoil configuration has its own characteristic drag force for the velocity. So in order to optimize the hydrofoil configuration, we need to work with the opt power. That's the power needed to deplete the battery on the predetermined discharge time. So of course, we have already optimized our propulsion system, so no matter what, if we sail at the opt power, we will deplete the battery on time. So we need to find the hydrofoil configuration that maximizes speed and still delivers a power inside of the range of the opt power. By this, we maximize velocity on time. So in order to do this, the algo is divided in 3 main parts. The first one is just a simple iterative calculation that considers the energy stored on the battery, the propulsion system efficiency, and the current solar recharge rate, and find that opt power for the desired discharge time. So the second part, of course, we needed to define the boat parameters. This is the equations that define all the design parameters of the boat. It's actually many of aerodynamic equations, and yeah, that's a little bit confused. So with this model, we can actually input velocity and input all the design parameters that we possibly need to optimize on our vessel. And then if you run this static model through all the design parameters that we possibly want to optimize, we will find the configuration that will deliver us the max speed for the opt power. By this, we maximize the distance covered in time. So the third part of the algo is actually this, the optimization algo that runs that static model through all possible design characteristics that you need to optimize, and then finds us the one that maximizes velocity and maintains that power. Of course, we are talking about millions of iterations, so we need to implement a convergence strategy in order to minimize the computational power. But I will not spend time talking about this. So you can actually define any vessel with any hydrofoils configuration in order to optimize whatever you want. It's just a matter of defining the design parameters on the static algo. And here we have our molds for build this beautiful geometry. As you can see, this is not a normal mold because the mold needs to match the twist on the foils in order to be possible to demold the geometry after production. So we need to find the surface that contains the plane form of the wing, and then we cut the aluminum block with the surface, and then we subtract the foil geometry from that surface. Can I finish? Thank you. So we get those 2 halves, and we just fill the halves with the gaps with carbon fiber. We use 2 layers of bidirectional on the first one, and then we just fill the rest one with unidirectional, of course, aligned with the span-wise direction. And it's just this. Thank you.
I was wondering, you were talking about efficiency. Do you have more data about what kind of improvement did you reach with this new solution?
I'm sorry for the time. I'm not good at manage the time for presentation, but here are the data. Of course, these data are based on lift line equations, so it's not 100% sure. But like with a CFD analysis, we can find that this geometry actually improves 30% the efficiency of the whole hydrofoil system. And actually is a bit more because this geometry is actually much more closer to the optimal case. So the lift line theory equations consider the optimal case, the ideal case. That is much, and these foils are much more closer to reality than the previous foils because of the separation bubble that we just showed to you guys. So yeah, that's the results.
And in terms of scalability, what's the limit of this solution in terms of length and weight of the boat?
Actually, as I said, it's just a matter to define the characteristics of the boat, more explicitly the weight of the boat, the position of the center of mass, and the position of the hydrofoils. Of course, you can implement another hydrofoil configuration, you can implement another, like many plumb form configuration, you can implement whatever you want. It's just a matter of implementing the equations and then makes the static model run throughout the configuration and find the one that is most efficient. It's actually pretty easy to model a different kind of boat with a different kind of hydrofoil configuration. As we just did for our new prototype, São Gabriel 01, that's actually an open sea class vessel. And it's actually worked pretty well, and it was really easy to implement the new geometry, the new characteristics of the new vessel on the Algo. So it's a pretty versatile thing. That's nice.
I'm sorry, I will be a bit pushy to you, but basically you explain that that's the correct way to design a foil, which is okay, but what is innovation?
Sorry?
I understood that is the correct way to design a foil by using the correct tool. What is the innovation?
The innovation is the Algo gives us the global geometry of the foil to the optimal case. So we will get the opt positions relatively to the center of mass of the boat. We will get the opt span length, the opt short length, to optimize the distance covered on the discharge time selected by the user. So it's just a matter of build the CAD on SolidWorks.
Then another question, you can answer.
That's a great question. We also wanted to talk about that. Pablo has been talking about the algorithm, but one thing that stands out in this design is that we don't use the traditional hydrofoil bulb configuration. We try to innovate in the sense that the bulb is, well, without trying to over-explain, the bulb is not the most aerodynamic shape. So it brings you a whole other set of problems. You may need to use ailerons or any other mechanism to actuate these foils because you can't move the bulb. So something like this, where you don't have a non-aerodynamic shape, you have something simple, twisted, and well put, is what stands out from this design that we came up with from the traditional one, and this most commonly is.
So what happens with the bulb is, the bulb cannot change the angle of attack, because if you change the angle of attack of the bulb, the flow will separate right here on the upper surface of the bulb. So it's actually not a, if you change the bulb for a wing profile, you can actually get the same results, but you also get active surface, because you can change the angle of attack without change so much the performance of the wing on that region.
Yeah, but I fully follow you, gentlemen, but your colleagues are doing that since few years, so I am asking the question, where is the innovation? I am sorry, but you did a good job, very, very good job. You used a good tool to design the good foil. This is okay. What is the innovation?
The innovation is the algo that find the opt dimensions to the wing.
Okay,
and
then it's okay.
The twist.
Thank you. Then it's okay. You answer my question.
Thank you, gents. We will now actually welcome our lovely Indian colleagues here from Team Sea Sakthi.
Check. So firstly, vanakkam, bonjour, and a very good evening to all of you present here today. My name is Roshan Manoj, and I have with me my colleague Hemlata. So we are Team Sea Sakthi from India. We come from a city in the south of India called as Coimbatore. So Coimbatore is known to be the Manchester of South India. Why? Because of the textile industry that it has. And in Coimbatore, there's a lot of schools and institutions. And one such institution, which has a 40-year legacy, is our institution, Kumaraguru Institutions. So we are a team of 13 students who worked on our project, our boat, YALI 3.0, for the last 10 months. And today, we're here to show you the innovations that we've done in our boat. So let's start with the cockpit. So the main problem statement that we had targeted this year was to reduce the weight as much as possible. One of our patrons, Commander Abhilash Tomi, who is also a sailor, once told us that every gram that we reduce is an advantage in our favor. And that's what we took seriously. And this year, we decided to go with pineapple fiber and carbon fiber as a sandwich layer. So we did test multiple natural fibers like jute, pineapple, hemp, and bamboo. But pineapple fiber gave us the best results with respect to the strength to weight ratio, the durability, and the marine resistance. And that's why we chose to go with pineapple fiber and carbon fiber as a sandwich layer. So this is the pineapple fiber, if you all can see. So for the next part, to talk about the boat, so let me give you a small anecdote before I start explaining, right? 90% of all composite materials used around the world is made out of fiberglass. And in this 90%, 20% is used for low load applications. And the production of fiberglass releases harmful substances like silica dust, limestone, and soda ash. And as you all know, the oceans are also being polluted with a lot of plastic. So we wanted to target these two problem statements and address it singularly. So we decided to go with upcycled plastic fiber for our seat. So what we do here is we take plastic that is around our campus, collect it, wash it, and then make them into strips. Then we spin them and weave them to form a fiber. And this fiber can then be made into a sturdy material for a seat. So by doing this, annually, we can actually reduce the amount of plastic being generated globally by close to 2 billion tons. So this is that innovation. Next, to talk about a battery. So basically this year, compared to the last 2 years, we're using a twin propulsion system. And for the twin propulsion system, the battery has a chance of overheating, and we did not want to take that risk. To take care of that, we decided to go with a passive cooling system with a mixture of expanded charcoal and paraffin wax. It's a very simple mixture and costs very less, so it's very feasible as well. So we are also using a BMS paralleling system this time, which makes it much more scalable for the needs of the day. And it's a 7:3 ratio, which actually reduces the whole temperature by 5 degrees Celsius if there is a chance for overheating.
So this year, we have made a remarkable strides in terms of embedded systems. So we have developed more than ever before in the previous competence. So to begin with, so this year we have introduced the advanced Yacht OS. So this provides the platform more similar to the Linux and Windows. Like in Windows, we do have like the inbuilt functions like media player and everything. So in case of Yacht OS, we do have a personalized dashboard. So that dashboard is not just only for showcasing or monitoring the real-time data. It also controls every single boat aspect and monitors the boat's performance. So one such main feature in the Yacht OS is the AI navigation. So in AI navigation, like if the pilot, we arrived like developing the solution from the last year experience. So last year, our pilot was struggling to see the buoys over him, and he couldn't find the optimum direction, optimum path. So this year, we introduced the AI navigation using the environmental sensors and shortest path algorithms. So by using this, we have derived the solution to AI navigation. And moving on to the second main feature, here comes the docking systems. So imagine your pilot is able to dock his boat without any help of his or her teammates' assistance. So he's completely independent on docking his boat, even in the narrowed path in the hard sea conditions. So this was made possible first using the IMU. It stabilizes the docking process. And second, we use the rear view using the cameras that is integrated with Python OpenCV system. And thirdly, we use the ultrasonic sensors to detect the distance between the obstacles. Like in car, we used to park our car, like we see left, right, the rear on the dashboard, right? So in the same, this applies the same. So this was applied in the docking assistance. So it just makes sure it's the safe and precise docking for the boat. And coming to the third main point is the pilot assistance systems. So it was inspired, like we used to talk to the AI, right? Hey Google, okay Siri. So the same in our boat. So imagine the pilot is talking to his own Yacht OS, like, hey Yacht OS, what is the weather today? Hey Yacht OS, what is the speed of the boat? So what other optimum directions I can take? So it's cool, right? So this was introduced. And coming to the biometric ring. So introducing the biometric ring. So this is nothing but the health monitoring system. So this tracks the stress, the skin temperature, the heart rate, so how many hours the pilot has slept last night, and everything it tracks. So main two reasons we have introduced is, first, it tracks all the live data to sense to the pilot so that he can be vigilant about his own conditions, and it's safety, of course the safety. So it takes all the real-time data to the offshore people so that they can also have an eye on the pilot, so to check whether he is doing okay or not. So this is about the biometric ring. Coming to the simulation, so this was inspired from the Gran Turismo, like where the players can experience a deep car racing experience. So in that way, we have used in the boat simulation. So we can monitor, like this, the environment reflects the conditions of the Monaco Energy Boat Challenge. So we can change the type of the propellers, we can change the weather conditions, we can increase or decrease the speed of the waves as well. So this is still in the research section. So we're about to implement maybe in the next year possibly. So this is about simulation. So if we want to get one component of like propeller, we have to go to one side of the country. For the battery, we have to go to another side of the country. So increased carbon emission. But if we implement this, no worries, you can sit in the room and you can simply like check the adaptability of your boat in various conditions. So this is about the simulation. So like a little construction cost for the technical side is around 19,000 euros. And the project cost is around 61,000 euros. And about the open source and the material, so all the materials have been uploaded in this QR. So I like to use the stage as an opportunity to call upon other teams to use the simulation, because we have made the foundation, so we need your help to work more about this, because we need better results, right? So please do use of this. And talking about the long-term vision, apart from the competition and building our boat, our primary vision is to empower the communities. So in that way, we have conducted many number of educational programs, creating the awareness to the youngsters and school students about the coastal communities. And yeah, this from my end. I'd like to call upon some of my technical students on the board to handle the Q&A sessions. Thank you. Thank you for your time.
Thank you very much for your presentation. There was many innovations there that I would just ask a question about the use of pineapple fibres. I've not heard of use of pineapple before. Obviously, I've heard of jute and basalt fibres and other alternatives to fiberglass. So I have two questions. Normally a sandwich would have a core in it. You didn't seem, are you using the pineapple fibres as a core? And I thought that would have affected strength. And secondly, how does resin react to pineapple fibres?
The core material is absolutely carbon fiber. We used a sandwich material of pineapple and carbon fiber to merge it, and we used a bioresin called IP2 resins to merge it. It's a marine proof too.
But did the pineapple fibres require more resin than any of these other alternative fibres?
Yeah, absolutely. It absorbs more resins. We use an vacuum injection molding to extract the excess resins.
Thank you.
Thank you very much for your presentation. I'm just coming back on the passive cooling system you're implemented. So it looks like a very simple solution that you've gone for. Why is this kind of solution not more widely used today?
Actually, the passive cooling system is most commonly used in the energy grids. We thought that we need a lesser, that the heat emit from the battery is comparatively very less, and the chance of overheating is also less. So we are still working on the battery side too. We are just in the phase of building our own BMS, and we just thought that the passive cooling system will be the first step to our innovation in our battery side. And BMS paneling would be like the scalable options, like for the future endeavors.
Thank you.
Hi, I was wondering, considering all the features you show, have you considered the amount of energy that you need? And the second question is, I believe that talking about sustainability requires an LCA approach. Have you considered these? Do you have some data about this approach?
Sorry, would it be possible to repeat the question?
The first one, if you have considered the energy amount that these features need, and how do you provide that?
So you mean the pilot's energy it's monitoring, or
it's
how much it's charging?
Electronic features.
Yes, so it's very similar to your Apple Watch or the smartwatches that's been tracking health all these days, and the only difference is that there have been researches conducted, and what we thought was the ring is more accurate rather than the watches, and it requires almost the same energy in order to charge as the watches as well. And as you said, to monitor the pilot's energy, that's available as well, because especially in races such as the endurance, it's very important that we measure all the important health vitals, such as the energy, and we monitor to see if the pilot's dehydrated or not, and we inform the pilot to drink water if he's more focused on the race.
Thank you and congratulations for all the innovation. We are very proud to see Indian team coming with all this. So very, very congratulations.
Thank you.
But as the other one, I will ask you a bit tough question. You are speaking about simulation. Okay, simulation is accurate if it's close to reality. So have you tested your boat? Can you give me an example about difference in between the simulation and the real test you have done?
Yes, so it's like he said, it's a very inspired product from a game called Gran Turismo, where a driver simulated, like he played the game and he went and raced in the formula. So why can't we do that? That was my question. So why can't we build boats and just implement all the material physics into the component, the simulation, and we simulate the product, simulate the boat. We don't need to go to another side of the country to buy the battery, as well as to go to another side of the battery to propulsion and to test somewhere else. We're emitting a lot of carbon emissions. So simulation avoids all of that. It cuts all of the carbon emissions. You can just sit at your home, like you can put in the weight of the boat. Yes.
This okay, but what is the percentage of accuracy in between the test and the simulation?
Right. So far we are still in the research phase, and we have so far we can change propellers and alter the weight and change the physics simulation of the water. So the accuracy is about 20 to 30%. So that's why I wanted to make this open source and get everybody's contribution, because every team faces a lot of different challenges. So if we can get all of the inputs, we can make a really accurate game such as the Grand Tour.
Thank you. And last question, because it will help my colleagues to give you the correct graduation. If you have to choose one of the innovation to try to have a good impact for the yacht industry, for your country, to sell the next generation, what will be the innovation you want to promote, and what will be the next step on this innovation?
If I may? Yeah, so I wanted to, so I was part of the embedded team making the yacht OS, so I'm a bit selfish. So I wanted the yacht OS to be part of the yachting industry, because imagine having yacht OS in the racing industry as well, and the boat racing competition improving, like E1 series. So if we have a common dashboard where the other teams can really have a chance to customize their own, to make unique product, and to race and compete, optimizing their performance, I feel like the yacht OS can really give a leap of chance for every team to increase the performance by a lot. So we feel like yachting industry and boat racing competitions can go to a higher level, such as the Formula 1. And this is just a start, and yacht OS can be a part of it. So to answer your question, he is part of the embedded team, so he's very selfish about that. But us being part of the mechanical team, we want to keep the pineapple fiber and upcycle plastic fiber. We want to do that. So
thank you.
Thank you.
Fantastic presentation once again. So let's move on with the Italians back again. Elettra from Uni Genova.
Thank you. Going forward or backward?
So, good evening, everyone. We are Elettra from Genoa. This is our second year participation, and with respect to the last year, the team is made almost by students, and the goals of this year was to enhance the configuration of last year by improving self-solution made by ourselves. We essentially rebuild the boat from scratches, since the 2023 boat was almost made by commercial solutions, and the first idea was to implement foils in our boat.
Foil technology is known to the ability to reduce drag and so increasing efficiency by lifting the hulls outside of the water. So we decided to study a foil configuration that was also reliable and that we can made it by ourselves. So we decided to use a self-stabilizing configuration. In the first trial, we thought that we could build like only one wing, but it proved to be too challenging for us. So we decided to check the market for off-the-shelf part. So with our calculation, we decided to use 3T foil in this configuration that give them the capability to be self-stabilizing. So the tips of the foil are very near to the surface of the water. So when the boat give a little bit of inclination, that part of the foil gives out of the water, and so reduce the lift on that part, stabilizing the boat. So our studies were started with the studies with the area, the total area, and the shape that we had to use to lift all the energy class our boat. After we checked the market, and we decided to design and build this specific type of attachment, so that can resist to all the weight from the foils, and so lift the hull. And we saw that with our calculation, we also ran CFD analysis, and we saw that with small speed, we received like a 10 to 15% in reduced drag, because the hulls were lifted a little bit, and so the wetted area is reduced, and with in about 16 knots, it's the highest peak of efficiency, with the up to 50% in efficiency. And along with this calculation, we also decided this year to design our propeller to get along this important change in the behavior and in the general configuration of the boat. And so we decided to print it. We decided to print it in PLA. And PLA was our also decision because of the sustainability of this material. And we saw that it was capable to do that, so we decided to go with this part.
And this year we had a common problem with the marine industry, which was weight. Already the last year configuration was very, very challenging to reach the maximum energy storage on board with the commercial batteries. So we decided to build our own batteries. We select lithium NCM cells. And in particular, we selected 45 of them, assembled in 15 series of 3 parallel cells each one. And we designed our own battery pack, starting from 3D design and 3D printing, because we had the idea that no ventilation was needed for our own battery pack, because with the calculation we made, just for leaving some space between one cell and the other, it was sufficient to not incur in overheating. Also because the cells we found has the most thermal diffusion with the bottom of the cells, and so with some tape, thermal tape, we fixed them on the bottom of the battery pack, and this was sufficient to not incur in overheating. Then after assembling our battery pack, we run some simulations at different charging and discharging rate in order to validate our calculations and to be able to monitoring correctly the temperature. And we managed to build the battery pack without any ventilation and refrigerating system.
Another important focus of this year configuration is the power delivered to the propeller in order to increase the boat performance in sprint races. Since our electric outboard had an 11.5 kilowatt nominal power inverter, whose IGBT do not allow an overload condition, especially because they have a very small thermal time constant. The idea was to replace this inverter with a more powerful one and test the overload condition of the motor up to 15 kilowatt for the sprint race duration. And the implementation required many thermal tests, but they showed the feasibility of the solution. The process started by creating a digital twin of the motor, which allowed us to simulate its electromagnetic behavior under the new operating condition. And then we set up a schematic of all the necessary connection of the inverter with the motor and the battery. Not only, of course, the power connections, but also the logic ones. And then finally, we were able to perform all the necessary tests, thermal and mechanical tests, first in our laboratory and then during dedicated sea trials. So, from an electrical point of view, this was our last year configuration, which was composed only by off-the-shelf products. And this instead was an hybrid configuration that we tested, only implementing the new custom battery pack with the BMS. And now, finally, this is our actual configuration, with, of course, the Énergie the new battery pack with the BMS, the new sensorless inverter, and the same motor that we used last year.
The wing configuration imposes us to make a lot of changes in the boat. In the reality, the boat was completely stripped out and rebuilt because also of the weight limit. So we had to also calculate if foils were possible in the weight range, in the weight limit. And so we had to lower the thrust plate to get the motor enough water on the propeller to get it to work it properly. We improved a lot the hydrodynamic part of our motor. And also, as I told you before, we worked a lot on the propellers that we tested in our tunnel of cavitation to check if the material, the PLA, was capable not to deform on high loads. And we saw that with our dimensioning, this was possible. So for us, it was a big leap. And so we was able to our propellers. And so the propellers in specific were like very different designs. Also we have a 4-blade one, so we also tried to change the number of the blades. And we used a technology that was really available. Like the 3D printer was not high-end or something like that. We used like a basic 3D printer to show that it is possible to also make this type of precise engineering with normal use machines. And this year was very challenging because we occurred in some problems. One of the biggest, I think, is the motor that we completely stripped out and changed because there's a lot of mechanical problems, and also the holes that were built incorrectly, so they were leaking, and it was very difficult to calibrate the foil configuration. Thank you for your attention.
Thank you very much for your presentation. I have a question about the foils, the foil configuration. I saw your drag curve, and I would expect, as you say, the drag to reduce as the speed increases because some of the foils come out of the water.
Yes.
But what are you comparing that drag curve with? What was your base case, your benchmark?
We modeled the hull and in the CFD. So we have like the basic structure is without the foil, so with the normal boat. So this was our reference point.
But did you look at other foil configurations? Because I would have thought...
Yes, we tried, we studied if the auto-stabilizing one were the best choice for us. because we didn't have the capability to build like a self-stabilizing one, and the T-foil configuration implies to have that to be safe, because in the T-foil configuration normally the boat tend to go out of the water without control. And also using off-the-shelf part in the foil with like the windsurf foil that we are using, the pitch is controlled by the weight of the surfer. So we didn't have this possibility. So we decided to use this configuration to be more safe and to be capable effectively to be self-stabilizing.
I have also a comment. First of all, compliments, because I think you're the first team in the energy class with the foils, so that's a very brave decision.
Thank you very much.
For what are you thinking to use it? So, for which competitions or which races?
One of the big problem of foils for us, but in general, is that we have like there is a lot of force on the structure that we apply with our structure. So if the sea is wavy, for us it will be a very big problem. So we are thinking about effectively using it during this competition, because it will be like not safe. So we have to protect the pilot, and so we will see. But surely the endurance race is the best choice for us.
One question also, if you can just go back on the slide about the lift on the foil. Have you considered the center of gravity and the application of the force? And are you sure that this is stable?
Yes. We tested it. We have like 80% load on the front wing and 20% load on the back wing. So the asset will be like a little bit up in the front and back lower in the back. So it's also like also for the shape of the hulls, that is quite dangerous, because they can like pierce into the wave and capsize. So we looked into it and we stay a little bit on the back of the boat.
Yeah, but also on the lateral stability, have you made some simulation?
Yes, we made some simulation, but we also checked it on the sea trial, and our foils they are not so high like on the solar class. They're a little, the height from the water is very little. So when the boat, in case of the boat really get the angle, the hull will touch the water, and so it will be safe.
Thank you.
Welcome.
Maybe another questions on the propellers. I think you are one of the few people that have the availability of the cavitation tunnel. So you designed your own propellers.
Yes.
And, how was the comparison? So you have a one-to-one comparison between the numerical model, or what is your design?
We saw that the numbers were something about 10% in difference. So we saw that the surface of the blade makes a lot of improvement. Also in theory, if the blade is very soft, not soft, but smooth, it's obvious that it's more efficient. But we saw with our tunnel that without polishing the blades, there are a very big difference in this.
Thank you.
You're welcome.
So we move on now to the special prize. That is the Monaco Energy Boat Challenge and the Prince Albert II of Monaco Foundation that have worked together to introduce this prize, named the Prince Albert II of Monaco Foundation Sustainable Yachting Technology Award. It's dedicated to recognizing and supporting outstanding initiatives presented by universities or research institutes during this Monaco Energy Boat Challenge. The winning organization will receive a grant of 25,000 euros to further develop and implement their solutions. We have 2 candidates, and we're going to start with the University of Antwerp.
Hi, good afternoon. My name is Matthijs from the UOP Solar Boat team. I'm very proud to be standing here today. We from the UOP Solar Boat team, at the heart of Europe, believe that the sustainable yachting can become different. As you all can see here, we have a huge mat with us. It is flex fibers. We want to produce new hulls made from entirely natural fibers to increase sustainability. We want to attack this problem at the source. As you can see on the slide, 97% reduction in material production CO2 emissions. So we want to attack the source and become more sustainable. Our project is built out of 3 different pillars. First of all, we want to promote sustainable materials, which is quite obvious. But a lot of times, sustainable materials or sustainability comes at a cost. But we proved that our solutions come cost effective. And last of all, we already have diverse applications currently in our solar boat, and we are improving further, and in the end we want to produce an entire hull out of natural fibers. Now, as you can see, we have a fiber mat with us. A lot of teams, I think everyone in this building uses carbon fiber. Carbon fiber is not sustainable, not at production and not at the end of life. We have 2 new materials, flax and filava, together with partners. Flax is basically just a plant made in Belgium. And then also filava is made from volcanic ash. Furthermore, we want to use, or we actually use bio-epoxy, which is also made from nut oil and is therefore more sustainable than regular old epoxy. Flax is really built into the roots of the UOP Solar Boat team and further into Belgium. At the 19th century, it started to become produced in Belgium. It had a downfall within the World Wars, but now it's really making a comeback. And it's easy to see why, because it's more sustainable. It is at the heart of Europe, so shipping and transport is quite cheaper than if we were to buy carbon fiber from abroad. The same is true for filava fibers, which is also locally produced in Belgium. Now, of course, we say we want to build a hull out of natural material. This is not really evident how. So we do fundamental material research. We research the strain and the stress of all the different fibers. We use different kinds of epoxy and different kinds of bio-epoxy. We research water absorption, which is obvious with boats, and also different kinds of production methods. From all this data, this is just one of the many graphs we have, but here we can see that carbon fiber is still the king. Okay, not too bad, but filava is a close second, and flax comes third. You might think, okay, we'll still use carbon fiber because it's really the strongest. But yeah, this is not always the case, because carbon fiber is often used just because we know carbon fiber works. We have developed a tool to know which material you should use and when. So you input the surface area of your new part. You calculate the needed strength your part needs and also the maximum thickness your part should have. Out of this tool, built in Excel just so everyone can use it, you get out a number of layers, of course, what type of fiber you should use and what type of epoxy and how much of that epoxy you should use. This reduces waste because you know exactly at the beginning what material you should have. So it's no more guessing, oh, let's just mix some amount of epoxy and hope that we don't have to waste a lot. I talked to you also about cost effective. As you can see here, filava and flax are cheaper than carbon fiber. And with a focus on less waste, which is also more sustainable, we also reduce cost at the beginning with our tool. So you have to buy less material. And we work with local suppliers at the heart of Europe, in Belgium. The 2 partners we work with work in Belgium, they produce everything in Belgium. And of course, I can say here, and we have all the data, but where are the use cases? Well, first of all, I hope you've all seen our flax decks. These decks are made from flax and polypropylene. These are, at the beginning, they are sustainable, but also at the end of life, because we just melt the polypropylene out of the flax, and we have the plastic and the flax again. We also have our flax cockpit, which is made from flax and also bio-epoxy. And this is a great example because, of course, our cockpit does not have to be the strongest item. It is totally ridiculous to make this out of carbon fiber. Therefore, we made it out of flax. And to prove that to you that even the strongest parts of the boat can be produced from natural fibers, we made our struts from lava. They're holding up. We have tested them many times, and they still work. So our new project is to build a sustainable hull entirely made out of lava and flax, which, by using our tool, we have less waste and become more sustainable. Currently, we have the different kinds of applications on our solar boat, and we are also implementing more tests, because for our tool, we already had more than 300 tests done. We want to improve this further to further improve our tool. And of course, we have a lot of work still ahead of us, a lot of hours that we will be working, but in a year, we will be done with this hull if we have enough financial help. So, we believe in a more sustainable future with the Antwerp Solar Boat team, with products created at the heart of Europe. Thank you for listening, and I will answer any questions you have.
If I can start, I have two questions. One is the life cycle analysis, global life cycle analysis. If you can give us some numbers about ideas about using flax fibers. And also, if you have some epoxy resin to recycle it. And my second question is, do you have in your test plan to test the flax fiber into the water? Because from all the tests we have done, and see Barbara also, we know that when we were using this kind of fibers, we were absorbing a lot of water and we were taking a lot of weight in the time.
Yeah, indeed. So to answer your first question, so flax, we have a reduction in 97% within the production, right? I don't know the exact numbers, but relative to each other. This is just basically because flax fibers are, it's a plant, it only needs water. Lava is a little bit worse because it still needs ovens, right? And carbon fiber is even worse. Still, at the end of life, we can't recycle everything made with epoxy. It's just impossible. But with polypropylene, we can just melt them out. It's in collaboration with different partners. The only disadvantage of this polypropylene, I want to be honest, is we only can make panels at the moment, so no curvature. Then for your water absorption, he's researched it, so I'll answer.
So if we are going to look at synthetic fibers, they have 0% water, and the natural fibers have 8 to 12% water in it. First, what we are going to do is take the water out, just put it in an oven at 40 degrees, and afterwards we are seeing that the natural fibers perform better without any moisture in it. So that's what we're going to do. And also we're going to coat our flex fibers afterwards, so no water can be in our material.
Thank you for your presentation, and I applaud your use of natural fibres. I think that's a big step forward, and I hope other people move to that. But my question is, I mean, there's a lot of work already going on about the use of flax and the use of basalt, and in fact there are production boats which use flax and use basalt. So my question is, what are you doing that actually will help to speed the uptake of the use of natural fibres?
Well, this comes mostly from our tool that we've been developing. We see that a lot of research currently only researches the tiny strands of these materials without any kind of epoxy. So it's still quite difficult to predict what behavior the fiber and the epoxy will have. Within our tool, we really just test all different kinds of configurations. And if we can make this tool public and add a lot of more materials and more epoxies, just the use of these materials will be more evident because you know exactly how this will behave, and that is currently not the case.
I want to like something extra about it. So in our team, we have a whole team that research all the different patterns of flex fibers, all the different strengths. A whole year we did tests on all different flex fibers. So this one here now is a twilled 4-4, but we have also tested UD, the plain weave, all the different weaves, and we have checked what's the best fiber that we can use to make our hull. And that information we also want to share with other people.
Yes, that is important, and it was part of my question. If you have this 25,000 euro grants, what you will do, what you will offer to anyone, and if you do not have these grants, what you will do?
So if we have the money, we want to further improve our testing. So more materials, more kinds of epoxies, and we want to make this tool public. It's now currently in Excel. We want to really make this just an application everyone can use. And we want to build our hull with this money to showcase that it's a possibility. Not only the data shows it, but really an example. If we don't have the money, we will go back to our partners, and because the partners already use our tool. And then we will try to talk with them and then further improve on the tool, and perhaps next year we can come back with more data to convince you guys.
If you are interested in the tool, I can show it later to you. Maybe we can talk about it after the presentation.
And finally, for our last tech talk of today, the second team in the running for this fantastic prize is our Portuguese colleagues from Instituto Superior Técnico. Welcome back on stage. Not on the schedule? All right, I have you on my schedule for today, but if we're not ready, then... If I'm not mistaken, we have a special prize as well tomorrow. Yeah.
Yeah, I'm wearing shorts. Okay, so hello everyone. Sorry for wearing shorts. I didn't know I was going to present today, but oh well. So today I'm talking about São Gabriel 01, which is our future boat targeted more towards more commercial use. A boat that you can look at and be like, oh, I could own this boat, I could have fun with it, and not like a competition vessel in its entire design, such as our Solar or Energy one. So yeah, this is the boat. I'll talk a little bit more about it now. So the first thing I want to explain is why we're doing this. So why is a team that already has a solar, an energy boat, and an autonomous boat doing to make a boat this size and this expensive? So the reason is simple. So we have knowledge in solar and hydrogen from our vessels, and we believe that approaching ourselves more to the industry is the correct thing to do. And we've tried to do that with the autonomous vessel, and it's been working out great. We really feel like more companies are interested in this idea because it has a future and a clear application in the yachting industry. And so we wanted to combine everything here and put it all in a vessel. That's hydrogen powered, solar powered, and as a commercial application. So the goals of this vessel are as follow. We want to reduce emissions, of course. The boat will have zero emissions. We want to promote the sustainability, show it around, go to different cities in Portugal, for example, show that it's what a zero emission boat can do and can be. We want to set a benchmark for the yachting future. To prove that this is the right solution for the future of yachting, have hydrofoils, have it hydrogen powered, and with solar panels. And finally, since we're all students in the team, we want to make this a learning experience for everyone. Because we feel like, in our university at least, we learn a lot about theory, but we also want to put our theory into practice. And this is one way that we have of doing this. So these are the categories I'll talk about in the presentation. So the solar panels, I'll talk a little bit more later, but the solar panels will be installed at the bow of the vessel. These are not directly connected to the propulsion system because the area is so small that it didn't make sense But this will basically just feed all the auxiliary systems. If the boat is stopped, for example, we can also use this energy to power the boat and not have the fuel cell on. We have the hydrofoils, which, as we've heard about a lot today, are there to increase its range and reduce its drag. And then we have the hydrogen fuel cell, which is our main source of energy for this vessel. And finally, we need to have a good energy management, because the battery will need to charge at very high power. If we stop suddenly, the fuel cell takes a while to slow down and decrease its power. So we need to have a good battery that can handle high power charging and discharging. So this is the problem we are attacking. The yachting industry is very pollutant. For example, a similar-sized combustion engine boat can produce up to 5 tons of energy. Up to 5 tons of CO2 each year, and this is only with 100 hours of use per year, which is the normal amount for a recreational boat. Also, the electric yachting market is growing, as we can all see. Each year in Monaco, we see more and more open sea vessels, and it's growing at an 8% rate year over year, which is very like a large percentage, and we want to attack that. And as I said before, we want to leverage hydrogen and solar power to basically to push the future of yachting in this direction. So our hydrogen fuel cell, we are targeting a power of 70 kilowatts with a consumption of 100 grams per minute. It will have an efficiency of 60%, which is more or less in line with all the other fuel cells. Since it's a very big fuel cell, high power, it will weigh 170 kilograms, which is normal. And we also want the fuel cell to have a large service life. Since we don't want to make a vessel that can only last 1 year, 2 years, we want this vessel to last several years, since the consumer doesn't want a vessel that lasts a very short time. The hydrogen tanks we have on board will work at a pressure of 350 bar. They will be type 4 tanks for the weight. We can carry 15 kilograms, which is a lot of hydrogen and more than enough range for Monaco competitions or for any recreational boat from the research we've done. The hydrofoils were designed to have a cruise speed of around 20 knots, which is very, very fast. And we can gain up to 75% efficiency depending on the speed of the vessel. These are also retractable for the simple reason of transport. We want the boat to be easy to transport on a trailer, and not need to use a crane when we are putting it in or out of the water. So that's why we have a retractable system hydrofoil. The solar panels have an area of around 2.25 meters squared, so very small, of course. They can produce a power of up to 540 watt peak. They are made in-house by us. And the efficiency of them is around 23%, already fully enclosed. They will weigh about 5 kilos, which is super light. We made them super thin, out of plastic, and they'll be on the deck of the vessel. The energy management, this vessel will operate on a high voltage. This is because there's no way we can make 70 kilowatts with like 48 volts. Just the current will be insane. So we decided to go to high voltage. Also, it's also what's used in the industry, and it makes sense for us. The capacity will be around 10 kilowatt hour, again, because we want the energy to be on the hydrogen tanks and not on the battery. The battery is only there to act as a buffer between the fuel cell and the motor. And finally, I want to talk, just before I move on, I want to talk about safety. Safety is a priority for us. We have worked with hydrogen, we have experience, and we know how dangerous it is. And now we are also working with high voltage. That introduces a lot of risks. So we are designing this vessel with all the international requirements. The whole design and the construction was made with the standards for a vessel, and we did all the calculations for the waves that hit the hull, for the deformation of the hull. So that's all taken into account. We will have isolation monitoring devices to make sure that the hull does not get electrified ever. And we will have leak detection systems on board too. The admin switches, emergency switches, lights that inform the pilot if the motor is on, so that we know it's safe. So yeah, safety really is a key priority in the design of this vessel. So the cost breakdown of the vessel is what's shown here. The fuel cell systems cost around 60,000 euros. The hydrogen tanks 15K, the hydrofoil system 15K, and so forth. At the moment, we have started to work on some of these aspects, but not all, because this, of course, requires a lot of money. And since we as a team already have 3 vessels, adding a 4th, the budget gets complicated, but we believe that we can have this vessel ready next year. So yeah, talking about the phases, phase 1 started around 2 to 3 years ago. We are past the design and the planning. We are now in phase 2, more or less approaching the end of phase 2 on the procurement and construction. We already have the mold, we have the fiber, we are missing just a few things, and we're gonna make the whole this summer. I'll show you some photos of the mold soon. Then we, of course, will integrate everything and test everything thoroughly to make sure that everything works accordingly. And finally, the phase 4, we'll just evaluate what it did, see if any future work can be done and what we need to change in the future. So yeah, the current progress is, you can see on the right, the mold that we have. It was machined with a 5-axis CNC out of 2 halves. And then it was coated in fiberglass to make it sturdy. So this is all made by us in-house, from the machining to the work on the molds. Everything is done in-house in the space that we have in University, which is great for us since we learned about this. But yeah, at the moment we do believe that approaching the more or less November, we should have the whole done, like the entire boat done, and just add the systems later on. And yeah, now I'm open for any questions from the audience.
When I visited you 5 years ago, I did not imagine that you will have done all that job, so congratulations. Something from my colleagues that might be important for you to share. Most of the time at Technico Solar Boat, you have an open source where you upload all the innovation, all the information. You are sharing all the development that you have. Are you applying exactly the same spirit with this boat?
Yeah, we apply it to all our vessels. We just don't share what's under NDA. We have some companies that don't like sharing documents, especially with fuel cells. But everything else will be open source, well documented, so that everyone can learn from it and apply it if they want to.
Thank you for your presentation. I have a question about the energy sources and how they're going to be used. Under sort of normal usage, how much energy do you expect to come from the solar and how much from the fuel cell?
Okay, so the solar, as I said, will only power the auxiliary systems. So navigation systems, maybe even some pumps for the fuel cell, for example. This is only 500 watts, so it's not much. At cruise speed, we should spend around 20 kilowatts from the fuel cell, and this will come directly from the fuel cell to the motor. And yeah, that will be it. Also, another issue of using the solar energy in the propulsion system is that since the solar voltage is so low, around 20 volts, 40 volts, for example, boosting it to 540 volts would have a massive loss of efficiency. So it doesn't make sense to boost it all the way to 400 volts to be used in the propulsion system. So we kept it simple, and it will only power the auxiliary systems.
So probably talking about 2 or 3%.
Yeah.
The solar, yeah.
Not much.
Obrigada para a apresentação. Same question that the other one, because it was a good question. If you have the grant, what would you do with the grant? And if you don't have it, what is going to happen with your project?
Yeah, so our main issue is money at the moment. Especially the fuel cell. Getting fuel cell from a single company is a very large investment from a company in the student team. And so we've been having issues with that. So what we do with the money will be simple. We'll acquire a fuel cell, acquire the hydrogen tanks. We already have some proposals and discounts from big companies that we know. So yeah, that's what we'll use the money for. If we don't get the money, I mean, we'll keep grinding on sponsorships, trying to get as much money as possible in order to make it possible. But yeah, for example, one of the things we made was a harsh decision a very hard decision to make, was that we couldn't get a fuel cell in time, even though we are it seems like a lot of time, 1 year. We are 1 year away from the completion of the vessel. We wanted to get the fuel cell sooner to start testing, and we couldn't do it. So what we did was we decided to make the vessel only have a small battery at first that will be used also on the hydrogen system. So this will be like a proof of concept that the vessel works, that we can make something that works. Maybe get some more attention from the industry to get some sponsorships. But yeah, that's more or less what happens when we don't have money. We adapt to try to get attention on us.
I have also a question regarding safety, because I think that with hydrogen, safety is one of the main issues, and how to integrate it on a boat that should go around with people that have no experience on hydrogen. How are you addressing this safety issue?
Okay, so the hydrogen compartment is well ventilated. We have fire extinguishing systems, automatic ones, in the hydrogen compartment and the motor compartment. We have leak detection systems, ventilations that automatically turn on if there's a leak, for example, and we also have natural ventilation. The hydrogen will naturally go to a point and escape. There are no spots where hydrogen can get stuck. That's impossible to happen. The tanks are also monitored. We monitor the pressure. We have relief valves in the system in case there's an unexpected increase of pressure, for example. We have lights that inform the pilot of what's happening. Simple lights, simple instruction on/off, very clear. The refueling system, we are also basing it on the current refueling system in hydrogen cars, copying it what's done in the industry, so that because they have tested everything, they know it's safe, and so we just adopt it. And in the future, maybe there are refueling stations in the marinas, and they'll most likely use that same system. So it made sense for us. So yeah, I think it goes more. My answer is more or less this.
Thanks.
Sorry. One more question. You partly answered my question. So it's proof of concept.
Yeah, it's proof of. We are a student team.
Yeah, and but basically the idea is to make proof of concept of a recreational boat, and if you want to set what you have done, calculation, everything, put on load, total load. What's the length of the boat?
Sorry, yeah. I forgot to say that.
Now, basically, how many people on board? Because at the end, all the calculation that you have done must correspond to a market, and this is why.
Yeah, so the length of the boat is 8 meters, 8 meters long, 2.4 meters wide. It will weigh around 1.5 tons with everything on board. It will have seating for 3 people. It will have a small space in the bow, like a room, we call it. It won't be a room in ours, it will be just a space, because making a room is very complicated and unnecessary for us. But I think those are the values that you are looking for. 8 meters long, 2.4 meters wide.
No, I go. That's so very important. I know you are a student team, but I am asking you more or less every year the same sentence. I know some of your past colleagues start their professional career in some companies. Are you considering creating companies or launching giving this plan to a yacht company or whatever, that all the development you will have done on that boat can be reused to have a real impact on the industry?
Yeah, so I cannot say that for sure. We always think about that. We thought about making a spin-off on solar panel manufacturing, for example, since we are really good at it, and we are running every year. It may happen in the future if we feel like this is a really good product that's missing in the market, and we have a really good shot at succeeding. We may do it, but the boat will also be open source. So if any company wants to come at us and talk to us about it, we are also more than welcome to show them all our documentation, and they can copy it, for example, and change some things, or if they think about that.
Thank you so much.
So, obrigado once again to all the teams that spoke today. We had some amazing concepts, and as we see every year, it's slowly getting better and better, and it's really contributing to the success of this industry and to sustainability as a whole. Tomorrow we continue with the Eco Conception Prize and the Special Prize. We will have 8 teams speaking tomorrow from 5 to 7 p.m. Be there or be square, and now enjoy the rest of your day back on the paddocks, and see you tomorrow. Thank you very much.